Silver is the world's best conductor of electricity, surpassing both copper and gold. Every year, more than 25,000 tons of silver are mined worldwide. But instead of ending up in jewelry stores, most of it powers the modern world in electronic chips, solar panels, surgical instruments, and much more. But have you ever wondered how silver actually comes to life? Behind every milligram of silver lies a surprisingly complex and demanding industrial journey. From raw ore buried deep underground, silver undergoes a meticulous series of steps: crushing, separation, chemical leaching, precipitation, electro-refining, and finally, shaping into usable forms. In this video, we'll take you inside the modern silver manufacturing process, from deep mines to high-tech smelters, from raw metal bars to polished materials that power our technology and touch our everyday lives. Silver is more than just a metal. It's part of the long journey of human progress. Mined for over 6,000 years, silver was once used as currency, a symbol of religion, and today it has become an essential foundation of the modern electronics industry. Beyond its material value, silver is a silent warrior in the fight against bacteria. Studies show that silver ions can kill more than 650 types of bacteria and fungi, including drug-resistant strains. Even in minute quantities, silver can break down cell membranes and prevent microorganisms from multiplying. Thanks to its powerful antibacterial properties, silver is widely used in healthcare, from antiseptic dressings to surgical equipment. With the highest electrical conductivity and light reflectivity of any natural element, silver plays a central role in the world of technology. In electronics, it is used to create printed circuit boards, connect chips, and transmit signals at lightning speed. In renewable energy, it is an irreplaceable component in solar panels, where every electron must move with precision and efficiency. In large-scale industrial mining, the extraction process begins with the expansion of underground tunnels, a network bored through the bedrock using specialized rotary drills. These machines are capable of penetrating hard rock with great precision, extending thousands of meters of tunnel each month. The drill head presses against the rock surface, rotating at high speed, gradually slicing through the geological layers like a giant mechanical blade. A hydraulic system allows the drill arms to adjust their direction, raising, lowering, or tilting to follow the terrain inside the mine. Once exploratory drilling identifies mineral-rich zones, workers drill holes and load them with industrial explosives. Each explosion is carefully calibrated, powerful enough to separate the ore from the surrounding rock, but controlled to preserve the integrity of the mine structure. The blasted rock is collected by heavy trucks and transported via elevators or conveyor belts to the surface. Every step of the extraction process, from drilling and blasting to transport, is monitored in real time from a central control room. Once transported to the surface, the silver ore enters its first processing stage, primary crushing. Visually, it looks no different from ordinary rocks, rough, heavy, and amorphous. But to extract the hidden value within, the entire mass must be standardized in size. This is where the jaw crusher comes in. It consists of two high-strength manganese steel plates, one fixed and the other moving, functioning like a mechanical jaw that compresses the ore between their sorting surfaces. The crushing action breaks the rock structure into smaller fragments. The deep grooves on the plates are specifically designed to control the rate of breakage and prevent the formation of excessively fine particles that could lead to the loss of valuable minerals. The system operates almost entirely automatically. Integrated sensors continuously monitor rotational speed, crushing pressure, temperature, and load in real time. The goal is to maintain a particle size range between 20 and 100 millimeters, small enough for further processing, but large enough to retain as much silver as possible. After leaving the primary crushing station, the silver ore proceeds to a more refined system, fine grinding. At the heart of this system is the ball mill, a massive horizontal steel cylinder filled with hundreds of hardened stainless steel balls. As the cylinder rotates at a controlled speed, the balls begin to move chaotically, colliding with each other and with the ore inside. These repeated impacts generate intense abrasive forces. No coarse fragments remain. What comes out is a fine powder with particles smaller than sugar grains. Every parameter, from the rotation speed to the ratios of beads and materials, including the precise amount of water added, is continuously monitored and adjusted by a central control system in real time. Once the ore reaches the desired fineness, the mixture is transferred to the flotation system, one of the most advanced mineral separation methods in modern metallurgy. Here, the slurry of mineral powder and water is directed into large, stirring tanks. In the continuous swirling motion, a small amount of reagent, typically yuxantate or a sulfur-based compound, is added to make the silver particles hydrophobic. Simultaneously, millions of microscopic air bubbles are injected from the bottom of the tank. The silver particles attached to the bubbles gradually rise to the surface and form a thick layer of mineral-rich foam. This foam is gently skimmed off and sent for further processing. Meanwhile, the clay, rock debris, and non-reactive impurities sink to the bottom and are carried away by a separate stream. After flotation, the resulting mixture is a silver-rich mineral mud that still contains a significant amount of water. To remove the excess liquid, the mud is directed into large settling tanks, where gravity takes over from the machinery. The heavier mineral particles gradually sink to the bottom, forming a thick layer of sludge, while the clearer water rises to the top and is collected for reuse. The concentrated sludge at the bottom, now with a texture similar to thick cream, is pumped into temporary storage tanks, ready for the next stage, preliminary smelting. After leaving the flotation system, the silver-rich foam is collected, thickened into a dense sludge, and transferred to the preliminary smelting stage, where the fire and metal begin to interact. The entire batch is placed in a specialized furnace operating at temperatures exceeding 1,000 degrees Celsius. The furnace, shaped like a rounded crucible, is lined with high-temperature refractory materials capable of withstanding sudden fluctuations in heat and pressure. Once the lid is sealed, the mixture undergoes purification by fire. As the temperature gradually rises, the mineral layers begin to melt. More reactive metals, such as lead and zinc, oxidize and rise to the surface as slag. Silver, being denser and more stable, sinks to the bottom, forming a precious, sediment-like layer. The entire process is monitored by temperature and pressure sensors. If the furnace is too cold, the silver will not separate completely. If it is overheated, there is a high risk of slag combustion and metal loss. In bar form, silver appears complete, solid, heavy, and well-defined. But inside, it still hasn't reached the level of purity required by modern industry. This is where refining takes over, a quieter process, but one that demands atomic-scale precision. At the refining plant, the impure silver is melted again in a modern induction furnace. The temperature and electrical current are tightly controlled. The entire operation takes place in a closed-loop system, equipped with recirculating cooling and sensors that continuously monitor the current, voltage, and crystallization rate. Under the influence of the electric current, the silver leaves the anode, dissolves in the solution, and gradually crystallizes on the cathode, which is now pure, uniform, and free of undesirable elements. Metals such as copper, lead, and zinc are deposited at the bottom as anodic deposits. After several hours of operation, a thick layer of refined silver forms on the cathode. While still in liquid form, the silver is poured into rectangular steel molds, each prepared as a predetermined location, shaping its destiny. This marks the beginning of the transformation of the molten metal into a solid form, typically reaching a purity level between 85% and 95%. The silver flows smoothly and evenly into the molds, its surface undulating like mercury as it begins to solidify. Temperature control at this stage is critical to prevent thermal shock, cracking, or the formation of internal gas bubbles. Each raw silver bar typically weighs between 25 and 30 kilograms and still contains small amounts of other metals such as copper, lead, or gold. This is when the silver takes its final form. It is no longer ore, no longer mineral mud, but a solid metallic entity. Beneath a thin layer of metallic dust in the small workshop, refined, seemingly complete silver bars begin a new journey. Each silver bar is remelted in a small-scale furnace, typically fueled by charcoal or gas. The shimmering silver is then poured into simple molds, rods, wires, or sometimes thin sheets. From these blanks, the craftsman begins the shaping process. The silver sheets are thinned by hand-cranked rollers, passed through repeatedly like dough being flattened until the desired thickness is achieved. The wire is drawn through a series of copper dies with progressively smaller openings, like wire and more wire, only with metal. For components such as rings, bracelets, or pendants, the artisan begins to bend and shape, a process guided not strictly by measurements, but by a feel for tension and years of experience. Once the form is established, the piece moves on to finishing, sanding, polishing, and sometimes engraving or marking. The final detail is often what the craftsman approaches most meticulously. Engraving names, setting stones, hand-carving designs. Each cut is a commitment, irreversible, unrepeatable. The silver at this stage is not shaped by complex machines, but by the steady hand of skilled hands. The journey of silver is a blend of industrial technology and artisanal skill. From anonymous ore to refined bar, from conductive material to custom jewelry, each step reflects the labor, technique, and respect devoted to this seemingly familiar metal. And now, let me ask you a real uncomfortable question. Is it normal that a metal essential to medicine, energy, and electronics is extracted at the cost of massive pollution and extreme mining conditions? Because ultimately, without silver, the modern world grinds to a halt. So, is this essential progress or a toxic dependency that we refuse to question? The debate is open in the comments. If you enjoyed this documentary, please like, subscribe, and turn on notifications so you don't miss any of our content.